Welcome to lecture number 2 for Stats 1. And this is a roughly 15-week course, basic business statistics, analytics. It's really a course in probability reasoning using statistics from a very elementary point of view. And if you look at lecture 0, ground 0, we're using just simulations. Actually, what we're doing is we're building these folks over here. Let's see if I can bring them over to join us. Yes. We're just building robots. Here's the modeler here. It has kind of a sour face. This is the 1921 play by Czech playwright Karel Čapek. And those are robots. That's all we're building are robots. We're building machines to do our bidding, and they will do our bidding, whether we realize what our bidding is or not. They will follow whatever logic we give them. And this is one way we, as human beings with rational consciousness, try to get at intelligible structures, intelligibility itself, and understanding of what's going on in front of us. The thing we're going to look at today, however, and I will not show a picture of this, is day laborer markets. And we have several here where I live in the Bronx. Many years ago, when I lived in Syracuse, I participated in such a thing. Now, what does it mean to participate? It means to stand somewhere at some corner where contractors will find you. And when they find you, they pick you, or they don't pick you. Usually have some sort of backpack with personal protective equipment in it. You better have steel-toe shoes. You better have the things you need to go, you don't know where yet. Painters, plasterers, people who are just digging ditches, people walking measurements, almost anywhere in the Bronx. Doesn't take much of an imagination to realize some of these places might not be so savory. And at the end of the day, you're paid cash. That's it. And eventually contractors get to know you, get to know where you stand on what corner at what time. So I frequently take a walk in the Bronx every morning, actually, almost whatever the weather these days. And I've begun to count the number of laborers waiting for a contractor to show up. At about 8 a.m. in the morning, this is Eastern time, come rain or shine. Rain or shine, clear, cloudy, cold, windy. I recorded measurements. I recorded the number, the count. I recorded whether it was precipitation or not at that moment, at that place, as I walked by at about 8 a.m. I checked my Garmin watch for the temperature this morning, for example, 30 degrees Fahrenheit, and the wind speed this morning, well over 20 miles an hour. I think it was like 24 miles an hour, whatever I wrote down. And I would write this down at home. Here is, as soon as I get in, I write it down. So these are my field notes, and I begun to code them. And I coded them for you. And that's what today's job is in this lecture. We'll put the RUR people over here. And what we're going to do ultimately is introduce ourselves to this guy. Yes, now there is a stunning stare. This is the Reverend Bayes. I'm going to look at his probability theorem. That is one of the most useful that we have in our toolkit. And again, it is a tool. And when we program, it's going to do exactly what we tell it to do. The thing is, we need to be clever about it. We need to understand it. We need to play with it. Okay, so goodbye, Reverend Bays. Put you over here for a while. And that's what we're basically going to do today. We're going to do some probability for real people. In the process, we're going to discover an insight using the very simple count the ways model applied to data that I have collected, and you can collect your own data. Some people observe the number of hawks, for example, during hawk migration season. You know, that's a Class A predator. Lots of hawks means some kind of environmental sanity is going on in the area. Utility companies used to have to measure hawks over their hydro resources, for example, to get an idea of how healthy, one of many indicators of how healthy things are. So we're going to try to find some intelligibility inside of these labor supply numbers. And this is labor supply from an economics point of view. And we're going to build a simple model, very similar to the model we built in lecture 1. And it's all going to be counting almost on our fingers. Part 2 of this lecture will put us into a spreadsheet again, where we will program, we will code that same model, and we'll be able to play with it because we'll make one of the parameters in the data. You'll have actual data. Oh my gosh, where is it? Let me show you the data. Oh, lots of stuff going on today. I think this is it. We're going to be building this model in part 2. And here's the data. The count and a coding of the climate going on, raining or clear, very simple, or snowing and clear. But I haven't seen any snow. We've had a little bit of snow late at night, but it's all been rain, high winds. In later versions of this, we will also look at temperature and wind speed as indicators of the count. Now, the thing that we're going to build right now as well is something called a threshold model. We have counts here far exceeding 5 or 6. When we say a threshold of 6, we mean at least 5. So, okay, or at least 6, something like that, depending upon how we code it. And some of these will be, yes, it's true, no, it's false. Okay. We can code that as well. But I get ahead of myself. This is the data. I already have the answers. So I'm going to kind of work backward from a data collection process and a sampling process to let's build a model, a structure through which we can, the lens we can use to actually see what's happening in this market. Okay, so some parameters, that's where that's going. And let's start right out with our 5-step approach. I'm going to eliminate myself here. There we go. And the first thing we're doing, let me make this black. Pose the question. I'm going to pose it this way, in a logical way. If P, then Q. And people usually do it like this. And that's a causal model. What is P? What is Q? The question that we're going to pose is, if it's clear, nothing else, just if it's clear, then will we see observe more than 6 laborers at an undisclosed corner or an undisclosed part of the Bronx? That's our research question. This is our data, actually. And we're also going to be able to get data on the laborers. But the data on the laborers is going to inform a hypothesis. And that's going to be very important to us. Okay, we're going to be building a very, very similar model. So, yeah, hypothesis. Let's look at that now. The second part is form hypothesis and make that plural. Claims, conjectures, ideas, a little bit more than just ideas. But the word form is extremely useful. Form is shape. We're giving shape to our question. Okay. And we often talk about shape when we talk about causality. We talk about form. It's like a blueprint, like a framework for thinking about it. So here's our framework. There's going to be 2 hypotheses. One, the count of the number of laborers is greater than 6. And exhaustively, we're looking at all of the possibilities, just like we did in lecture 1. We looked at all the possibilities. There we looked at the proportion from 0%, which was ludicrous, to 100%, which was ludicrous, for the object of our inquiry, which is Earth. It's not 0 water or 100% water. Okay. 0 water is the moon. Okay, that would be quite reasonable. So again, we've got to think about our hypotheses in a reasonable sort of way. So we just don't let things happen here. We just look at it in a reasonable sort of way. And if we look at the data for the laborers, the lowest number was 1. 1 actually showed up. 1 person showed up in extremely cold wind chill weather. I mean, it's just ridiculous that somebody has to work like that, in a position to have to work like that. If you've ever done day labor, and I have, it is dicey to say the least. And again, there's a community, they're all male, by the way, community of brothers that are just, I suspect, supporting one another. Usually go off in groups of 2 or 3, couple of lone wolves here and there. Something to be studied, because the numbers are increasing, I'm told, and I'm beginning to see this phenomenon at other corners that I happen to pass. So it's growing, it grows with the economy. Okay. So hypothesis 1, greater than 6, again, informed by what I have seen, and less than or equal to 6. And I'm writing it this way because that's how I'm going to write it in Excel. So I have 2 hypotheses. Hypothesis 1, hypothesis 2. And again, this is a count. Equals, in statistical parlance, the frequency. The frequency. Frequencies aren't percentages. Frequencies are counts in this business. And I continue with tremulous hand here. But there's a couple of things to note about the hypothesis. First of all, they're mutually exclusive, but they're also exhaustive. MECE. Okay, we have a complete story here. No double counting of or overlap of these hypotheses. And if you do intelligence work of any kind, government intelligence, business intelligence, and so on, these are called competing hypotheses or alternative competing hypotheses. They're in full competition. Okay, they're head to head. Okay, and that's not just a term of art. It's a pretty technical way of thinking about this. So the third thing we did, we sampled data. I think we have 19 observations. We can look at a minimum, a maximum of each. We have 19 observations, and the count data has, I think, a minimum of 1 and a maximum of 32. And in another lecture very soon, we are going to look at a way to summarize data, especially count data or continuous data like temperatures or wind speeds. Those are continuous data. Right now, we're using categorical data coded as binary. That's the kind of data we have. 1 or 0, R or C. Greater than 6, less than or equal to 6. These are all coded binary. The most basic data we can possibly imagine in our part of the universe. Okay, so we sampled the data. I showed you that data. Now I'm not going to show it again. We'll look at that another time. And then we finally get to count the ways. Well, now we have to build a little model. And what are we counting? We're counting two sorts of objects. Okay, this is what our fevered imaginations are doing, by the way. Two sorts of objects. Let's come over here. One is we're going to be looking at combinations of R and greater than 6, C and greater than 6. Well, we could do that. We could also look at R and less than or equal to 6, C less than or equal to 6. These are joint counts, jointly happening. And we need to find in the data, whenever there's an R, is there, yes or no, 1 or 0, yes for 1, 0 for no, is there a count greater than 6? That's what we need to find. And if there's a C, is there a count greater than 6? And similarly for less than or equal to 6, less than or equal to 6 in both cases. Those are joint. Now, the other thing that we will concern ourselves with is not just joint. We're going to call these marginal, not because they're marginalized. They're actually in the margin of a table. Okay, that's why they're called marginal. We're going to look at the count of how many R's are there, the count of how many C's there are, the count of how many times we find counts less than or equal to 6 or greater than 6. Okay, those will be called marginal counts. And in the world of probability, these, when we look at these relative to the 19 total observations, these counts become joint probabilities and marginal probabilities. Well, the fifth thing we'll do is, we will get to this, is we will do something with all of these counts. Okay, but right now I want to build a model, and it's going to be a tabular model, and it's going to look like this. Very similar to yesterday. We have hypotheses here. Greater than 6, less than or equal to 6, a little box around them, visually appealing. Okay. We have data up here, clear or rainy, precipitous. I'm going to include snow in that definition when I write that up someday, if I write that up. And that's data. I'm just calling data D and hypotheses H. Now, we're going to have little count boxes in here. We're going to count literally intersections, the jointly occurring hypotheses, specific hypotheses, and specific data. Okay. Now, I promised also marginal counts. How many times do we see counts greater than 6? Well, that's going to occur whether it's rain or shine. There we go, there's that one. And that is literally the count of greater than 6. We already have that over here. Just putting it over here for reference purposes. And in this box, it's everything else, less than or equal to 6. Well, if we could do it for hypotheses, we can also, and this is the anatomy of this kind of a model, we can see how many clear days there were by counting up this box plus this box equals that box. That's all the C's. And we can count up all of the rainy or precipitous days. And that's the box. Well, it had better happen, and this is a great data check, that if we count these jointly occurring boxes of C in greater than 6, R in greater than 6, C in less than or equal to 6, R, and all of the ones that are also less than or equal to 6, they better all add up to 19. I already know they have to add up to 19, so I'm going to go ahead and do this and hope I didn't do any double counts. But it's also true, if I go down this way, that the number of counts that are greater than 6 plus the number of counts that are less than or equal to 6 had also better add up to 19. Told you, this is just going to be counting. Okay, lots of counting. And all of the C's plus all of the R's have to also add up to 19 in the other direction. Let me just put an arrow there just to emphasize that point. Now, it's interesting. We can either go across the hypotheses or we can go across the data. And we only have 2 kinds of data here. Now, doing some counts, going through it, doing some sorts. Actually, I did it also in Excel, and I'll show you that in part 2. I come up with, and of course I don't remember all these things. I come up with, let me pop that in here. 11 times we see both clear days and labor counts greater than 6. Okay. And 2 times in the data. So this is really important. This is given this data at this particular point in time, 8 a.m. in this particular season, going, I didn't tell you when it actually occurred. I think I started off at 12/27, December 27th. And the last observation was January 18th. And I was sick in between. I had a booster, COVID booster, and I wasn't able to go anywhere for a few days. So there's a few days that are missing. Okay. They were probably bad weather days too, so I was too unhappy there. But that's what happens. There's going to be missing data in the state. So all of those things are assumptions of the analysis, the start time, the end time, any time there might have been a problem in the data, a lacuna, a gap in the data. All of that's important. And interestingly, it happens to be 3 and 3 here. And we can fill out the rest of the table because all of the C's have to add up to, and they do add up to 14. All of the rainy days, there's 5 of those. 14 and 5 do add up to 19. Check that off. And this is just a 2 by 2. Some of the scenario analysis I have done for clients, there might be 8 or 9 hypotheses across lots of data categories, some binary, some not binary. So you can imagine the cells of this table. It's called a contingency table, by the way. In this way, it's a 2-way contingency table. Goes both ways, across and down. Kind of, that's right. It's also called an association table. And this is bread and butter. If you don't like bread and butter, it's oil and vinegar, salt and pepper. This is basic to analysis, that you associate 2 things, okay? Your data and an hypothesis. Well, without any further ado, the number of counts that are greater than 6 are 11 and 2. And that better be 13. Yep. And less than or equal to 6. Well, 13, take away that from 9, had better be 6, and it is. So the model checks out. So that's our first step. We've got that done. And we go like, okay, now what are we going to do with it? Okay. We can actually express all of these as fractions of 19. Okay. Fractions of 19. And that's pretty useful. Let's do that here. Just going to make another table over here. Move this whole thing down. And then, let's see if I can copy this. And one of these is paste. I hope that's it. Nope, I don't want that. Well, it didn't work for me today. I'm just going to get rid of this. Okay, let me, I got to work on that skill apparently. All right, so we can put all of this in the form of fractions. I'm going to let you do the arithmetic. I'm going to scrunch up the table a little bit. Well, that's interesting. If I did this visually, I'm just looking at data, right? You see that? Okay. Data fans itself across hypotheses. Well, we're going to go over here. And the typical table will look more like this than with these cells separated. And let's see, I wrote down some notes so I don't have to do any of this. Check this out yourself. 58% of the time, we will see observations of clear and greater than 6. And if it's 13 divided by 19, that's 68% of the time here. So figure it out. What is the joint relative frequency, and we'll call that a plausibility, of seeing both R and greater than 6? Well, it's 68 minus 58, right? They have to add up, because everything's being divided through by 19. That is 13 and 11 and 2 are all being divided through by 19. That's their anchor here. Well, this has to be what? And I think I got one of these wrong. Oh, it looks close. 52. Yeah. So gonna have to bear with me here. This has to be 10. And if this is 32, and this is 26, the probability or plausibility of seeing just rainy days ends up being 26%. Oops, I'm sorry, I already jumped the gun. That's 16, 26. Okay. I always tell my students, I'm not responsible for the arithmetic. You are. Make sure it's correct. Yeah, check it out. Okay. But 10 and 16 better add up to 26. And so what's this got to be here? We can either look at it 32 minus 16. And that makes sense. They should be the same because it's a count of 3 in each case. And 58 and 16 gives me that very tremulous box down there. 74. What's 74 and 26? Everybody? 1. What's 68 and 32? Everybody? 1. So again, it checks out. Okay, so this is the probability point of view, where we have simply calculated the number of greater than 6 and the number of C, see how many of those are jointly, divided by the total number of observations. That's the 0.58. That was equal to 11 divided by 19. Okay. So we have counted the ways. Now that's a big step here. We have probabilities. We have a probability model now. Probability for real people about real people in a real situation. It isn't completely encapsulate their situation. This is just looking at understanding that data. We're almost asking the question here, how bad does it have to be for people not to show up? Okay, that's another way of asking. Or how clear does it have to be, glass half full, for people to show up? 6 people show up. And talking with a couple of the folks briefly, yeah, contractors want to be sure that there's enough people there before they go there. Enough people of the right skills. So counts like this matter, thresholds like this matter, conditions that influence thresholds matter, okay, from a practical decision-making point of view. And if you don't work, you don't eat that day. It's as simple as that. Okay, so we did joint counts. That's what's in this cell, and this cell. These are now called joint probabilities. And as promised, there are marginal counts. 68% of the observations are greater than 6. 32% are less than or equal to 6, or at least 6. And down here, 74% of the days that were observed were clear. 26% of the days, the rest of the time, were rainy or precipitous. Okay, so there's our basic counting model. Now we're going to use this model to do a couple of things. We're going to come back over here, and we're going to move on to the next step. What was the next step? We counted the ways. Let me load the step up here for us. We counted the ways. Now we're going to infer answers. Answers to what? The question that we posed. If it is clear, then will we observe greater than 6 laborers? Okay, I think we got all of that there. We have clear, greater than 6 laborers. So if what we're actually looking for here, the plausibility, this is what we're looking for. This is what we're trying to solve for in this question. The plausibility or the probability that greater than 6 occurs given conditional on if it's clear. That's what we are looking for. And this conditional statement is this kind of a conditional statement. In general, it's the probability of an hypothesis occurring given particular data being observed. So this is evidence. This is yes, no, and it isn't just yes and no. It's really maybe. Because we never know anything for sure when we do probability analysis. Probability is we just don't know for sure. And we're looking, grasping for straws here at how plausible one hypothesis is competing with another hypothesis. And we're going to need a way to characterize that. And the way we're going to characterize that is we're going to look at the relative plausibility of this hypothesis, which is our main interest, relative to this other hypothesis. Now, if there are 45 other hypotheses, it would have to be this one hypothesis relative to all the rest. It's a pretty tough thing to look at, okay? Competing hypotheses. Or clusters of hypotheses relative to others. See, there's a lot of ways to manage this knowledge. Knowledge happens when we make a judgment. We affirm that something probably is or probably is not, having grasped the data. Now we got knowledge. Now we can, that's inference, and learning is inference. And then we update the data. I will come back here in a couple of weeks and throw new data into this and see if it's any different. And is this new regime of data different than the old regime of data? I can do that as well. So a lot of things I can do. I can also go to other corners and compare, because it's all common size probabilities now. I can compare their greater than 6 with the other greater than 6, one corner with another. 2 sample, multiple samples. You probably get the drift. But I want to compare greater than 6 to the plausibility of less than or equal to 6, also given this data. This is called an odds ratio. It's the probability of something occurring divided by the probability it doesn't occur. This if this is, I'm sorry, I'm going to use P for probability here. We're going to use it pretty soon. And the thing is, these two probabilities, that's all we got. Okay, that's all we've got. Now, how are we going to do this? Well, we have everything we need to be successful here. Let's put this up here and reconstitute this. We're answering this just one question today, and then we're going to cut and run and go to part 2, at which point we will expand on this a little bit. But today we're just going to ask this one question about this one plausibility. Okay, and this one plausibility, here it comes. Here are the hypotheses: greater than 6, less than or equal to 6. And if you write this down enough times, it becomes like second nature. And coordination, proprioception. Yeah. After a while, muscle memory, neural imaging through our central nervous system, working together with our mind. Marvelous combination, but it also create a lot of bias. So we break it by doing things like this, called a habit. Yeah, lovely. And habit formation is a really important thing that we study in a lot of fields, in business and outside of business. And we know that this is what, 11 and 3? Yeah, 11 and 3 is 14. Okay. So I want to make sure everybody's paying attention here, including me. 11. So we saw a count of 11 laborers in this category of greater than 6. Okay, it happened 11 times at the same time, jointly with one data point. The data point was it's clear. Okay, one data category. I'm sorry. 11 times it's happened in the observation, 11 observations. Less than or equal to 6, okay, 3. And when you add these up, as we want to do right now, our total universe of discourse only includes 14 observations. So that's our total now. We don't care about rain at this point. And that means 5 observations are just eliminated from this question immediately. So it is no longer 19 total that we're dealing with. It's only 14. And if we look at the probability in terms of counting the ways of, if we have a total of 14 possibilities for clear, and 11 is allocated to greater than 6, and the rest, 3, is allocated to the rest less than or equal to 6. Okay, what is the probability? Back in black here. PR for probability. That the hypothesis greater, how plausible, better, how compatible with the data, even better. Doesn't prove a thing. This is not a demonstrative deductive argument. This is an argument from probability, from plausibility. Very different kind of argument. Doesn't prove anything. It indicates, it suggests. Yeah, okay. Given, clear. Well, we can write this very simply as the number of greater than 6 and seeing C divided by, Now, this is going to be interesting. I hope you find this interesting. The total, which is the number greater than 6 and C plus the number less than or equal to 6 and C. No, not a 6, C. Okay. That's the frequency way of looking at this. And if we do it this way, you see it's 11. I'm doing it the hard way, I know. Divided by 14. Now, 11/14ths. Do your math. I think is 79. Well, it's a high plausibility, but high relative to what? Well, if there's only one other what, and that is, we can cheat here. Remember, all probabilities we only have 2 here, add up to 100% or 1. So the rest of it is 3 out of 14, right? So the probability of less than or equal to 6 given clear is equal to 3 out of 14. But that's also equal to 1 minus 0.79, right? Check it out. Check it out. See, these are the constraints on our model here. We're constraining the model. We're constraining the robot that we're building, and we're paper and penciling the robot. Well, electrical charges running through my pencil here. That is. So 1 minus this ought to give us what? Got it? Got it? Got it? Got it? 21 maybe? So when you compare these two, which one would you think is more plausible? The one in which there are more ways than the other. That's all we're saying is reasonable. That is our definition of reasonableness, of intelligibility. Bingo. You could take this as a philosophy course, sure, no problem. Epistemology 101, stats 101, but this is practical, very, very practical. Okay, so let's summarize it over here. 3 over 14, and that's equal 79, and the rest of it is 21. Now, the odds makers among you, probably 1 or 2 out there. Human beings, by the way, tend to think more, and study after study shows this here. This is how humanoids think. This is how machines think. All right. When a lot of psychological experiments have been done over the last about 25 years, and I remember one even much longer in the 70s that I observed. How do people process this kind of information and formulate and solve for the hypothesis, which is what we're doing? It's like an algebra problem. We're solving for the hypothesis. Going a little bit roundabout here. They use the scheme on the left to do it, if they do it at all. There's a lot of biases in this. They often choose the wrong one for some reason or other. Like 8 or 9 of those reasons. Don't think in terms of probabilities. But we're going to do both because we're just, I guess, masochistic about this. No, we're not. We want to look at all the angles. And now the odds ratio is literally just 11 to 3, which is the same as 79 to 21. Why? Well, if you divide 11 by 14 and divide 3 by 14, that's the same as 11 over 3 times 14 over 14, which is the same as times 1 times itself. So it's all the same thing. And if we do this, what do we come up with? Roughly 2 to 3 times. You can do the calculation yourself. Suppose it's 3 times. I'll show you what we're going to do. We'll actually do it over here in the analysis. 3.67 times is what that answer will be in part 2. 3.67 times as plausible, probable, plausible, reasonable, more intelligible. Likely, we tend not to use that one because that's a kind of one of those reserve words, statistics and probability. But yeah, I would use it with a client. Compatible with the data is probably the most correct. 3.67 times as compatible. Well, that ought to finish us off right here. So try the probability of greater than 6 given the other option, R. What does that work out to? I promised you Bayes. Oh, you're going to get Bayes in part 2, but we just use Bayes rule theorem. I wouldn't call it a law, but we've actually found out something really important: how to compute a conditional probability. You can also, by the way, not as easily, but almost as easily compute the probability. So we want to be able to compute this. I shouldn't have done that. Let's do this. There we go. Now we got rid of that. Okay, cool. Greater than 6. So this is the other way of looking at the world. Data given an hypothesis. We'll be using this later on, this idea. But if you go over here in the counts, instead of going vertical, you go horizontal. I think it's 11 and 2 and 13, right? So we would be formulating our ideas this way. Okay, because we're looking at an hypothesis. Given this, we want to focus on that. So we're really looking at that cell. But greater than 6 occurs across both C and R. That's all of the data. Okay, and that's the probability or the count of the hypothesis. What would it come up to? 11, 2, and 13. 11 times that happened jointly. 2 times that happened jointly. For a total of 13 times that we see counts greater than 6. The probability here will be 11 over 13. And what's 11 over 13? Well, don't have a calculator on me, can't think about it too heavily. What's 1/13? So 11 to 13. 11 over 13, I think it's, I don't know what it is. Let's do it like this. Equals 11 over 13. 84. Make it round it up to 85% of the time. 85% of what time? 85% of the data. Will account for or be compatible with plausible, it's plausible, 85%, that's the plausibility rating of seeing a clear day given that very first hypothesis. So we have a method here. We have a way of thinking about it. And this is when I get into a tizzy over, and I often do, over conditional anything. It turns out that when that happens, I go to this model and it clears it up immediately for me. Okay, if I get confused about what's conditional on what and what am I talking about and so on, boil it down to this basic mind model, and you've got it solved. You go horizontal, you go vertically, and we have something called conditional probability that we're dropping into. And this is our first shot at it. You're going to need multiple shots through this in order to make it work. I'm going to leave you with that. Turn it over to part 2. Enjoy your day. And again, thank you very much for your very kind attention. As we finished, what do we do? Lecture 2, Probability for Real People, part 1. Okay. Thanks again.